University of Tennessee and the National Institute for Computational Science, which is kind of at the University of Tennessee and kind of at Oak Ridge National Labs, which does weapons research, on the community multi-scale air quality model used to simulate ozone, particulate matter, toxins, visibility, and acidic and nutrient pollutants. But basically they're doing what that Excel spreadsheets do, just on a far bigger scale.
Sounds like a local TAC introduction of the speakers. Hi there, folks. It's the top of the hour. We're going to give it probably 2 minutes yet before we get going. I'll start with an introduction of our first speaker.
It's the students. Boy, he lets them have it.
He has never done that to our class.
I'm going to go ahead and mute.
Consider yourself lucky.
I feel...
Presentation mode is now enabled.
Okay, I would like to welcome everyone to the February version of the ECSS Symposium. This is our forum where our ECSS experts share some of the things that they've been doing on the projects with their user groups. So our first speaker today is Kwai Wong from the University of Tennessee. Kwai is going to be talking about his work with Principal Investigator Joshua Fu, also from the University of Tennessee, on the Community Multi-Scale Air Quality Model. And what I find interesting about this model is the ranges in scale. So this is looking at air quality from ranges starting from urban, so you're talking about kilometers, to intercontinental, to thousands of kilometers. And so how you're able to bridge these types of scales, I think, is very much a supercomputing application. I'm interested to hear what Kwai's been able to do here. The focus has been, in particular, on the I/O. You know, as you imagine, especially when you get to the fine-grained scales, that's going to be a real problem. And what Kwai's also been involved in is he is mentoring one of our Campus Champion Fellows. So Nasir Idrisi from the University of the Virgin Islands is working with Kwai and the PIs on this project for a year and kind of seeing what it's like to undertake an ECSS project and how you go about such things. Nasir has the background also in environmental modeling, more with an ocean slant, I would say, at University of Virgin Islands, but it's been a nice pairing. And with that, I will turn the floor over to Kwai. Thank you very much, Kwai. Oh, also, if folks have questions, you can either use the chat feature on the web conference, or I'll open up the lines at the end of Kwai's talk. There's some background noise, so I have everybody muted right now except the speakers. Okay, take it away, Kwai.
Thank you, Nancy. This is a project that it has been going on for more than a year, and in this particular talk, so what I'm going to concentrate in presenting some of the I/O analysis that we have done with this particular model. So this is a air transport pollution model, and so it's kind of important because we have the weather and the climate and all come down together. We also would like to see how the pollutants, CO, CO2, and all those things go. So I'm primarily working with the team to sort of study some of the method to optimize the code. How can we do some of the workflow a little bit better? Particularly, there's a lot of I/Os in here, so we'll take a very good look of some of the I/O issues in here. So Jiaxiu Fu is the domain scientist, and David Wong is actually a gatekeeper of the code, and he is with the U.S. EPA and Research Triangular Park. So Cheng En is one of the very hardworking graduate students that we are working with to get some of these data out and running some of the code and help out the entire team. So this is an important code because it helps to define using the analysis to define some of the regulation and maybe be able to foresee some of the policy that the politicians or in local, state, or even the federals can do in terms of how things are affecting, like what kind of input budget that they can take for industry, particularly in terms of exhaust and things like that. So the model can do quite a different things, and particularly can simulate ozone and PM 2.5 is the target right now. Some of the toxic chemicals that can transport to somewhere, and from that point onward, some of the nutrients, some of the pollutants throughout the atmospheres. So the model of the scale, as Nancy has mentioned, that it's a multi-scale, so it goes from a few kilometers and to regional and to mostly, and the largest one they can use right now is intercontinental. So it goes from small scale, medium scale, and then to large scale. So if you look at the core code of the CMAC code is basically doing a lot of chemical transport. So we need a meteorological modeling system, typically the climate model, the WRF, and some of these input data, and they have a module to translate some of these the data input. And of course, there are also some input. I mean, you have to have a budget input, so the location of the power plants, and what kind of exhaust they are putting in. So it's very important. So once you set this initial condition and the boundary condition, you can start this model. So to get this model in perspective, the very first thing is of course you have to have a budget of the pollutants, or the budget of the exhaust, or budget of the transport. So that is a very, very important thing. And then, of course, you have some emission system modeling that gather all these data and then put it in this model. So you have some gas phase chemistry, and of course, you have some advection effect due to the meteorological model, some diffusion effect, some of the aerosol and depositions, and some of the cloud chemistry also. And at the end of it, they comes out and then you point out some of the charts and do a lot of different analysis, and then they can report this analysis to a certain target, and maybe perhaps guide some of the politicians to do some of the policies in terms of emission control and things like that. So in this particular part right here, we are putting our effort into the I/O. So the I/O, in fact, of this model is sort of has a very long tradition of it, and because it's a widely used model, so the I/O has a very fixed structures, and it's been using regular net CDF and do it the XYZ, and then the layers, and then in terms of, and also many variables. So it is very, in terms of changing the format of the I/O, it is almost impossible, because a lot of these users across the country or everywhere in the world, they already have these kind of data, particularly collection of data of data input and things that in terms of this format. So what we really like to see is, based on these legacy format, or this type of format, and the legacy I/O code that they have, the I/O interface that they have, can we do some improvements? So basically, we got into with Joshua and also the gatekeeper of the code, David, and there's another Wong right there, and so we work together and try to look into if this code is going to put on a large supercomputer, a medium-sized supercomputer, and how does it affect? We would like to sort of give the user a certain guidelines for certain size of domain, for certain size of computer or facility that they have, in what sense that they can expect in terms of the I/O of this code. So the basic test, if we take a look of it, is this graph right here. We do very simple graph. If you use the red line is just regular net CDF, and the maximum MIMO time in this particular case is let's say is an average of 80 seconds, something like that. But if we switch it to parallel net CDF, and we get a sort of down to about 20 seconds. So these kind of effect is very important, and because of the time scale of simulations, we can run this code for long times, and depends on the size of the input and also the size of the grid size, and sometimes the I/O amount can take from 18% to 28%. So it's a substantial part of the simulation in this particular case. So if we look at the domain-wise, so basically in this case we just taking a very particular domain. We have a small size domain like California, and it's 89 by 134. So it's a column, row, layers, and then variables. Typically there are 146 variables. You can see there are a lot of variables in there. And the horizontal resolution is 12 kilometers in this case. It can get smaller, as you can see that if the resolution getting smaller, then the amount of I/O, the amount of computation will continue to grow. And so in this particular case, we only take 3 time steps. So we build a test code, and we try to see what kind of effect and what kind of data that we can get out from this particular case study. So the I/O module, as what it is used right now, the regular I/O module is just using regular net CDF, and what we're going to do is to explore some different methods. So the very natural way is to upgrade the net CDF to a parallel net CDF, PNet CDF, and we try to look into the domain-wise when these the entire domains are partitioned in certain types of domain, and see whether we can collapsing some of the data. And then, of course, if it is running multiple time steps, and we would like to see that if we're collapsing the time steps and aggregate the time step result, can we get better throughputs? So we'll look into 3 different type of machines, and basically all these machines has a Lustre I/O subsystem built into it. So the very first one is a Kraken, which is in NICS, and Kraken has it's a 40 OST, the I/O subsystem. And we have Newton. Newton is a very small clusters. So basically a lot of small institute, they use a small PC clusters, and Newton is in about 1,000 cores processors, and they also have some parallel I/O system, but it's a very small Lustre I/O system. And then we also got into running some of the analysis on Hopper, which is available in Lawrence Berkeley National Lab. So Hopper is a little bit different machines. They have a larger I/O subsystem. Also, the user base is a little bit different. So we'll look into all these things. If we look into, if you look at the methodology itself, I mean, of course, what we really want to do is the key point is to get very big throughput. I mean, if you look at the basic idea, in order to get a very good throughput, it's really writing a lot of data contiguously. So that is the basic principle, is can we arrange all these data in such a way that we can write them in a contiguous fashion in a big chunks, okay, without violating the existing format of the I/O. So that's the bad part of it. Is literally we cannot change the format of the I/O, but based on that, we want to make sure that all these we can write a lot more data, within a certain time. So we have this slides right here explain the 4-way. I mean the top left, right? We have the NetCDF regularly. So basically, what is existing right now is is aggregate to process 0, and process 0 basically is just write out all the data in that particular format. So you would imagine that if you have a large number of processors, then this thing will probably not as good as you think. So the parallel CDF is just okay. How about we change the function call a little bit? We just call parallel net CDF. Let the basic subsystem taking care of it, and every processor output. Then the third way is called collapsing. The collapsing is we look into the data and look into the way of the decompositions. Okay, if it is decomposed in such a way, is there something that we can help to collect the data a little bit better in such a way that we don't have to do a I/O from every processor? So one group of the processor will do the I/O, and that group of processor will get out contiguous data accordingly. So the last one is the time collapsing. Okay, they say that, all right, if we want to improve the performance, one way is to make the data write out larger. So every time you can print out contiguously, writing out a larger amount of data. So though in that way, we should improve the throughput rate. And so we try to collapse all 3 times that result, and we want to see what kind of things that will happen. So we'll start to present some of the results in the following. So we have to test some of the strike size effect, and if we look at this, so we did some of these tests right here using 1 megabyte and 2 megabyte, and we find out that, and also the 60 megabyte and 4 megabyte. To a certain extent, the best performance overall is about 1 megabyte and 2 megabytes. So it's sort of in that particular range, about 2 megabytes. It depends on the domain size and the number of processors. But if we want to present a number to these users and what particular number you want to choose, then we would say that in general 1 megabyte and 2 megabytes will do a good job. Okay. Then the strike count. So the strike count, of course, depends on the size of the simulations. So in this particular case, we choose a 2 megabyte, and we have strike count 2, 4, 8, 11, 40, and 160. So on Kraken itself, we know that we have 40 OST, and so if you go to about 40, you are probably reaching the limits of it. So we do a series of tests and then present the result in here. It looks like in this case, strike count about 10 or 15 probably will do the work on Kraken for this particular case. So this particular case is the medium size output. So it's the Eastern United States. That's the medium size of the test. Okay.
Kwai, what do the processor the processor grid label there? What does that mean? The 8x8. That's not total processor count, is it?
So 8x8 means 8 times 8 processes. 8x8 processes. So that's
okay. So like that. So the ideal scaling for this problem is 64 processors. Exactly. Okay.
So you can tell that this is with this particular grid size, and so the 8x8 is pretty much reach its limits right here, right? So, but depends on the size. So we are running the 12 kilometer limits. If you shrink the 12 kilometers, then your grid size is going to be very large, and depends on the continental U.S. or the eastern U.S. Then it will be different, and depends on the number of variables that you want to output also. Yeah.
Thank you.
So there's a reason that they do that. It's 8x8 is because we'll explain a little bit later why we say this 8x8, 32x32 instead of just saying 64 or 1024. So these are these slides are just some of the things that we have done on Kraken. So basically, the maximum strike count, and we probably skip through some of these slides. So if we look into small domain. So small domain, let's say just, if you're just interested in California, 12 kilometers is the grid size, right? You can go down the grid size a little bit, right? So then if you look at the output for the regular net CDF, it's about 10 seconds, and whatever number of processes that you do is not going to affect much. And if you look at the PNet CDF, and for a process size of 8x8 or 8x16, you probably reach about the maximum plateau of 16x16, so you get about 10 seconds. So it's because of your size of the problem, and the I/O is not scaling anymore. So you can see that if you are using PNet CDF and go all the way to 32x32, simulating a very small domain, you are wasting a lot of time just doing the I/O. Okay. Then we have the collapsing code, and surprisingly, we see that the collapsing code is scaled pretty well, and it's pretty steady. I mean, if we look at it, even though we use a very large amount of processor, and the I/O time is staying about the same. I mean, and it's about 5 seconds. It's very comparable to other ones. Okay. So, of course, I mean, we're just talking about I/O time in here. If you want to do a lot of simulations and you cut down the I/O portion of it, the other portion of it, if you use more processor, then the computation can speed up with more processor. And that portion of it we have not presented yet. So, but we just look into the I/O. So you do gain something if the I/O time is sort of stable itself, and you can choose a larger amount of processor, and you are not paying the penalty of it. But of course, your ISO efficiency will sort of go down. So for the medium domain, if we use regular NetCDF for this particular case, and you can see that now the I/O is going to getting to be more significant because you take about 80 to 100 seconds throughout of all these processors. And then the PNetCDF, you can see that it's starting to improve. And you can see, for example, in 8 by 16 and 16 by 16, with larger amount, a certain medium-sized amount of processors, you get only about 20 seconds. So the collapsing code, if you look at it, wow, it looks a lot better with the 32 by 32, because if you can see it for this, even for this size right here, the 32 by 32, the I/O time is almost the minimum of it. It's only about, I would say, about 5 seconds in here. So you do gain a lot in terms of the I/O efficiency in this case. But for the time collapsing, now we can see that some of these things are getting a little bit worse, and particularly beyond the 16 by 16, and you're not seeing any gain at all. So it's kind of surprising that in the beginning that we looked into this data, we thought the time collapsing will help us because we want to aggregate more data so we can output it. And it turns out that when we analyze the amount of data, the way they write out the data, they have to write out every time step specifically. So the way they read it, is very rigid, and they have to write out every single time step. So even though you collect 3 time step, aggregate 3 time step, they will write data not in a contiguous fashion. It's in a fashion that is sort you have to jump around to the data format to the next page and things like that. So it seems to be because of the rigidity of the data format, the time collapsing scheme cannot be efficiently used in this particular case. So let's look at the large domain. So we can see that a lot of these effects are a lot bigger in the large domains. You can see the NetCDF is a lot, bigger, and the PNetCDF is getting a lot better, right? And then the collapsing scheme is a big winner right here in this particular case. So as the size of the grid size, the amount of the data that you have to write out is getting larger and larger, and the collapsing scheme is getting a lot better. So this is the I/O module efficiency chart that we can see that the collapsing scheme is really helping out a lot. The reason that we find out is because in general, the data, when they chop up the domain, they chop up in column-wise. So the collapsing scheme, if we do a 32 by 32, we only collapse to 32 processors in the column-wise. So everything is writing out contiguously in that column fashion for one variable, and then continue for the other guy to write it out. So that particular way, we can, use the communication switch to pass all the data to the head node, which is in contiguous fashions, and then instead of using a lot of write clients, we just limit ourselves in perhaps just 100 clients, and then we can see the efficiency is the best in the particular I/O case. Yeah. So we also do some machines in the Newtons, and the Newton is a small machines, and we can see some of this effect also, but not as severe as as what we've seen in Kraken. And the reason is because the I/O subsystem is not performing as efficiently as Kraken.
Just a few minutes left, Kwai.
Yes. So if we look at one particular slide, the particular slide is to compare the efficiency of Kraken and Hopper. And we can see that Hopper is, in fact, doing a lot better or doing the similar ways, and we can see that this type of schemes are very transparent. I mean, as long as we can have a good I/O subsystem with a parallel I/O subsystem, we can certainly migrate these schemes and be used on all different kind of machines. And some of these things even doing a little bit better in hoppers, because hopper seems to be there's not a lot of noises around hopper, because there are not that many users at one time on hopper. Okay, so these are just a typical slide, but you can see the particular trends of what we have observed. So this is the last slide, and so if we were to recommend something to the user in the community, we said that, okay, if you choose, you have a parallel I/O subsystems, and you want to quantify some of the numbers, they say that, okay, the strike size of 1 megabyte and 2 megabytes, okay, and the strike count is maybe about 10 to 15, and that should be good enough. And if you have larger OSD, like for example the new big machines right here, you can potentially go a little bit higher, but to a certain extent, to about 15, 20, or 10 to 15 to 20 is about the good numbers. And the collapsing parallel net CDF is as we find out that this is the best way to do your computation. So if you have a small machines, like if you're just using a very small machine like clusters, and then even doing some of these methods like PNet CDF will also improve your performance. Okay. Nancy, that's all of my talk.
Kwai, thank you very much. Let me open up the phone lines here.
Presentation mode is now disabled.
We have time for maybe one question from folks on the line. I have a couple of things came to mind for me during the talk. One was kind of the general applicability of parallel net CDF and whether that ought to be something that we maybe give a training class for users on Exceed systems. And is the collapsing aspect of that, Kwai, that's very specific to this particular code?
Exactly.
Yeah.
I mean,
okay.
The reason is because this code has been using net CDF, so we do not want to overhaul the entire I/O format. So it's an EPA code, and so they have a lot of policy if you want to distribute out another version of it, things like that. But the idea is really based on the contiguous of writing data. So any time you want to write data, you want to make sure that it is in a contiguous fashion. In whatever way you can arrange it, in this particular ways, because of the decomposition, and we can collapsing it in a certain directions. So it's try to minimize the number of write clients. If your number of write clients is getting over 1,000, then you are going to have contention in the network. So this fit in the general criteria of how do you optimize the I/O.
Right. Yeah, sounds like a very good approach.
Yeah.
I wonder what it was like. So our next speaker, Carlos, also mentions working with a legacy Fortran code. This code also seems like it's been around for a while. I know that can sometimes be a challenge for our ECSS supporters. Did you find that to be an issue working with your code?
So we only are interested in the I/O module. We don't seem to have a problem because we work closely with the gatekeeper of the code, so he's very familiar with the code. But we work in the sense of telling him that these are the particular things that we need to put effort to it. And first of all, we have to understand what the data structure, how do they write out these things. And once we understand how they write out these things, then we just implement the PNet CDF. From that point on, we'll also implement some of the collapsing schemes. So I think it's most important to work with the developer, and they know what the user requirements, and developer also know some of the criteria, and then we can just make some changes for them.
Right, very good. Thank you very much for taking the time to prepare this presentation for us. Very, very interesting. Very nice results. Congratulations.
Thank you very much.